Okay, well, let's try a Newton's second law example, remembering that Newton's second law is the net force equal to the mass times the acceleration, where both force and acceleration are vectors. So that means we have to add things and match things as vectors. So x to x, y to y, or any sort of coordinate system that we choose, okay? So what do we do when we solve problems? Well, step 0 is always don't panic. So let's take a deep breath. And then we'll read through the problems for our knowns and unknowns and any clues. We'll draw a picture. We'll label the picture with those knowns and unknowns, and then we'll figure out from our equation what we need to do to solve. So getting started, reading the problem, we see a worker is applying a constant horizontal force. So I'm going to use everything in force should be red, so you can keep track of it. So this is a constant and horizontal force, and it has a magnitude of 20 newtons, okay? So because it's a vector, it has a magnitude of 20 newtons, and horizontal tells us its direction. We also see we have a box of mass 40 kilograms. It's resting on a level, freshly waxed floor with negligible friction. That's pretty important because that means there shouldn't be a friction force here. Most importantly, we want to know what is the acceleration of the box, and that is our unknown because that's what the problem is asking, okay? So in order to get started and use these things, we're going to draw a picture. So that means we want to start with our floor. So here we have the floor, and we're going to add a box on top of the floor, but first we're going to add sort of some visibility to the floor. Okay, and then we have our box. So we'll draw a box. All right, there's our box. We'll make it a little bit less. Oops. Fill it in with a slightly lighter shading. All right, so we now have our box. Let's make it purple. Why not? Okay, back to gray. Okay, so we also have a worker. So here's our worker pushing the box. He has little shoes. You don't have to necessarily draw the worker, but sometimes it can be fun. So just for context, we have to figure out what forces are acting on this box. So the first one that's obvious is the pushing force, right? And, oh, we've made it blue. The pushing force pushes in this direction. That's where the worker is in contact with the box. But remember, when we're talking about forces at this level, we're really just talking about treating the box as a point. So we're going to sort of on top of this diagram draw our free body diagram. So that means our pushing force, remember vectors you can move anywhere. Pushing force looks like this. So this is F push. Okay. What other forces are acting on this box? Well, we know it has a mass, so that means it has a weight, right? So this is going to be its weight, and the weight is equal to mg. It also has a normal force. The normal force can be drawn here normally, but we're going to put it on our dot because remember, we can move vectors anywhere we want as long as they stay the same size and direction. So we have a normal force, we have a pushing force, and we have a weight. Now you'll notice in the up and down direction, right, we have two forces and there's no motion in that direction. So that means the acceleration is probably 0. And in this direction, we only have one force, so there's nothing to cancel it out. So we can take a pretty good guess that we know the direction of our acceleration and it's going to be to the right, okay? But even better would be coming up with a coordinate system for our problem so that we can really do vectors. And so we're going to call this axis the y-axis, and then we'll call this axis the x-axis. We don't have to do anything fancy here because this is a pretty straightforward problem, okay? So now that we have our x and y axis, and I'm going to make them dotted just so they don't get as distracting in our picture here. We want to write down some of our knowns and unknowns. So we know that our F push, that's going to be 20 newtons. We know that our mass is equal to 40 kilograms, and we can also write that this is frictionless, because that's pretty useful. And we know that we're looking for our acceleration, okay? So now we actually go back to use Newton's second law, right? So this is Newton's second. And the reason for the vectors and the sums is that we know if we sum up all the forces in the x direction, notice these aren't vectors anymore because I'm using the subscript, we have mass times acceleration in the x direction. If we sum up all the forces in the y direction, that's mass times acceleration in the y direction. But right away, we know if we sum up all the forces in the y direction, that's going to be normal force and weight, right? And because we know up and down on our y-axis, that's going to be normal force, positive, minus weight, which is mg, negative, is equal to mass times acceleration in the y direction, which we've already established to be 0 since there's no motion in the y direction. So we can actually write our y direction stuff as normal force minus mg equals 0, which means that the normal force is equal to the weight. That's kind of not an issue here because we're really worried about what's going on in the x direction. So in the x direction, we only have one force, that's F push. And it's equal to mass times acceleration in the x direction. But I'm going to leave off the subscript because we only have one acceleration and it's easier to write things without subscripts. So now we have two equations, but we only really need this one because as we know what F push is, and we know what the mass is, right? And we're looking for acceleration. And so we're pretty much ready to go on this problem. So we just do a little bit of algebra. We say acceleration is equal to F over m. Well, that's going to be equal to 20 newtons over 40 kilograms, which you hopefully can do in your head. 20 divided by 40, that's about a half. So 0.5 meters per second squared. That's our acceleration, that's our magnitude of our acceleration, but of course acceleration is a vector. If we look over here, we can see this is pointing in the x direction, the positive x direction. So if we want to write this as a vector, you can either write an x hat, which indicates a unit vector pointing to the right, or you can write to the right, or you can use I hat, whatever makes you feel good, or you could even write positive x direction. All of those things work just fine, but remember, acceleration is a vector, so that means you'll need both magnitude and direction, unless the problem specifically asks for something else. I'm going to try to draw a box here. Oh, it's a weird box. And it's deleted everything, so we'll get rid of that. And we'll make this a little bit thicker. So that's our answer. And because it's acceleration, we'll make it orange because we try to keep consistent with the book. That means orange for acceleration, green for velocity, blue for position and displacement, and red for our forces. If you have any questions, let me know. If not, we're going to move on.